Yes, sir. Yes, sir. Sure.
Good morning, all the participants. I welcome you once again to this Northeast Center for Technology Application and Reach Nectar sponsored 1 week online entrepreneurship development program on flexible 3D printing operation and prototype development. So we are really pleased to have amongst us Dr. S. Shiva from the Department of Mechanical Engineering, Indian Institute of Technology, Jammu. So before starting off the session, I would just like to brief you about our speaker for today. Dr. S. Shiva completed his BE in Mechanical Engineering and ME in Production Engineering. He has attained his PhD from IIT Indore and was pursuing his postdoc at IIT Madras prior to his tenure at IIT Jammu. Additive manufacturing and laser surface processing are the key areas of research of Dr. Shiva. He has a number of reputed publications in this line with good conference proceedings and book chapters. He is also having an Indian patent for one of his products developed by Shape Memory Alloys. He is also the recipient of the prestigious Newton Bhabha Fellowship funded by Royal Academy of Engineering, London, out of which he was working as a visiting researcher at the Institute for Manufacturing, University of Cambridge. Apart from his academic experience post his PG, Dr. Shiva has industrial experience as well. Currently at IIT Jammu, Laboratory of Advanced Manufacturing and Processing is his research lab, and his team possesses 3 PhD scholars and 2 JRFs. The team is continuing active research in the line of additive manufacturing and utilization of high temperature alloys. So with this very brief introduction, I would like to invite Dr. S. Shiva to start off the session. Sir, please.
Yes, sir. Thank you. Thank you, Professor Das, for that kind introduction. It's my privilege to be part of your program. Thank you very much for this opportunity, first of all. And good morning to all the participants. So this is Dr. Shiva. And as I said, as Dr. Das gave in the intro, like additive manufacturing has been my area of research actively, like almost for the past 10 years, almost a decade. Like when the next year we are stepping into a decade where we had been collaborating with RRCAT Indore, and we started this research in fabricating smart materials. Specifically, our focus was in functional materials like shape memory alloys for certain applications where they can be utilized in the line of MEMS, like MEMS, for micro actuator applications. That was the first step towards our journey in our journey. And as things frequently prolonged, we started pursuing our research thoroughly in using utilization of additive manufacturing in the various aspects, like not only in functional materials. Then we went on with high temperature alloys, which is now actively being looked by many of the industries, and as well as our national research labs like ISRO and DRDO. So we are assisting them in certain projects which are lively going on as well from our lab. So today's talk will be focusing on the types of additive manufacturing techniques for respective applications. So the fact behind this is like, what is generally people think that 3D printing and additive manufacturing means. Immediately things come to their mind is the image which is shown here in the first slide, like a type of laser based setup, and they use a high power laser where powders are being utilized as raw materials. And as this powder utilization, you can say that utilizing these powders and by using this high power lasers, the 3D printing process is being carried out using coaxial feed. Now, similar to this, certain groups are also actively have been establishing themselves in the line of wire-based 3D printing techniques. So, apart from all this, it is not that additive manufacturing is being restricted only these two domains. So, to give and shed some light in this particular aspect, first I will be starting with an intro and the different types of AM which can be utilized and the challenges with the methodology, successful applications which is going to invite industries towards additive manufacturing, and finally you will be having the conclusion part. So generally in the aspect of manufacturing, if you check, this is the normal design flow chart or the design process chart, you can say in other words, which has been conventionally used by several industries for decades. So when you say industries for decades, like initially, once the industrial revolution started, slowly lean manufacturing started to take place, like effectively utilizing the labors, and like basically the manufacturing revolution or the industrial revolution initiated. Much focus was provided not only with the technologies that are to be deployed for development and the products that are being used as output of that effort, but also sincere efforts were put on standardizing each and every method. Like, for example, if an industrial unit is there, there has to be certain principles to be followed and there has to be certain protocols to be followed. So, anything related to these particular principles and protocols, that is where gave birth to this sort of process making chart, where a new prototype is to be introduced from the industry. First, there will be a detailed markets research, it has to have a clear-cut information about what is the customer's demand or like what is it, what are all the types of expectations from the customers. And once after deciding the types and the demand, the next thing will be how hot is that particular market. Like it is not something like we have certain requirement, we are fulfilling them at certain needs, and it doesn't mean that we are reaching the dead end immediately, because when industry is being established, it is a paramount effort and huge money investment comes into picture. So in that case, what happens is that first principle will be like time is money. So whatever time they have to much effectively utilize without much of wastage. That is point number one. Second, there are other principles like utilization of materials. So whatever raw material they procure, the best amount of utilization or like the maximum amount of utilization of raw materials will really assist the industry to be in the safer side rather than just putting out their more overhead into picture and just bringing an chaos in the financial management of the system. So that is the reason why this sort of sequential protocols are framed in the form of charts after detailed literature of after making a detailed literature survey about the principles of industrial management as well. And as an effect of those efforts, slowly the output started, lots of brainstorming sessions came into picture, and they framed that these important steps, these 10 steps, which are to be followed before any type of prototyping, and each and every step will have its own specialization, specialized engineers to be precisely said. And once these specialized engineers come into picture, they will be putting their full effort so that that particular domain does not cause any sort of misleading or like any sort of malfunctioning in the entire process chart, because even one segment of this entire chart is going to be like it commits any sort of errors, either be manual or fatigue or whatever it is, that is going to cost much for the organization, and that cannot be borne up unless or until an organization is completely set up. So that is why they started with first a proper design team functions, like what is the product that they are looking for prototyping, and how optimally the product can be made in efficiently utilizing the raw material by minimizing the wastage. And once if that particular program is done, next comes the analysis team, like the proposed methodology. This is what is the methodology which is being proposed by the synthesizing team. They will just cross check. It is just like a check part, and eventually it comes to the document drawing. So before stepping into the shop floor, you need to have a proper documented drawing, including the POQs and all the other details, so that by seeing or like having the drawing that is being documented by the first level of design team, the production planning team will just decide what are all the raw materials that they are about to plan, they are planning to procure. And once after that procurement is done, how effectively the entire process has to be continuously running without any shortage of raw material, because once the shortage of raw material comes into picture, then the entire job is going to be halted, and that will eventually land in trouble for the industry. So this particular planning has to be done, then followed by the raw material procurement, because availability of the raw material plays a very, very crucial role in this particular segment, because there are certain raw materials that maybe that our country may not be able to afford, or like it has to rely on any sort of and foreign overseas supplier. So how frequently the supply can be made, whether it is affordable, all these parts will be done. Second, followed by the tool procurement. So tool procurement is nothing but it is thoroughly done by the manufacturing engineers in the shop floor. Like what sort of tools are required for this, for the functioning machine, either it's going to be manual or CNC. In case of a CNC based work, we also have to ensure that the proper programming has to be done, and followed by this programming, and the output will be generated. And this product, before launching to the market, will be followed by a QC inspection, where quality control team will be taking over, and they will check whether they will check right from the top level, like from the design segment till the production segment, whether the product is meeting up with the design drawing, and whether the design is being properly done, or if there is any fault in the piece while it is being manufactured. So all these steps will be detailedly analyzed by the QC team, and then once they give a go, it goes for packing and it jumps into usage. And it is not just stopping there. Obviously, once the first set of products are floated to market, you will be finding that there has to be a repeated feedback collection process to be done. And why is that being primarily focused is, once the feedback is being obtained from the customer, that will be assisting the industry to release the next version, or it will just facilitate the industry to evolve itself in a better way to meet the requirements of the customers in a better standard. So these are the basic functioning that it will be done. So once when you bring in additive manufacturing, these following segments, like almost out of 10, you will be surprised to know like almost a half of that steps are getting skipped. So this is a huge success for any industry, because we are not skipping these steps by compromising their job, but just with the existing 5 steps, the steps which are cut short are also to be taken care then and there, so that that will save time, save raw material, and also save the overhead cost in the form of manpower. So this is where additive manufacturing started taking the world by storm, and this is where a true justification was provided for utilizing additive manufacturing in an industrial level. So that is the point where the new revolution started taking place, it can be said. So once after that is done, so okay, how this can be done? Like for example, if in case of an additive manufacturing, you can see the synthesizing job and the analysis job can be done by the design team initially with their CAD drawings, followed by immediately they can generate the CNC program, that is the G codes, which is used for printing an object. And all these selection like tool procurement will be off the show, raw material procurement and planning, they need not just wait. It is all like fire and forget. Once they order for any bulk set of raw materials which has to be stacked, that is a periodic process that will be done. You need not go for raw material procurement for each and every segment. That will be part of a continuous flow. And the QC can be skipped because the facility that additive manufacturing provides once they are in the set of manufacturing, like it has to be like you can check in an in situation monitoring technique can be deployed, so that if there is any sort of error, then and there, as the fabrication process is being carried out, you can just check and rectify the errors in the precise way that it has to be done. Next, rectification is another detailed topic, but anyway, the surface level I'll be covering in today's talk as well. And there is no requirement for any sort of drawings with BOQs and this other details, because the drawing itself can be customized at any point of time just by altering the program. So this is how sequentially the cut short of steps in the conventional design process chart came into picture. And as an effect of that particular step which is being taken out, we can see that how this is being deployed in application successfully. So here, this is the first step where the synthesizing and designing is done, where a solid model, where a 3D object imaging is being done. And as an effect of that, next they will be directly placing it for the laser processing, where the powder materials are being procured, and the several slicing works which are required for as per the program step-by-step analysis. Like you say, layer by layer, the layers are being finalized in this particular step. And then once the process is initiated, you will be finding the final component ready for utilization. So if we check the entire functioning here, you will be finding that there is a type of 2 kilowatt fiber laser which is being used as a power source, and that will be like introduced, or like it will be made to interact with the raw materials, which is powder. And these powders are basically like you will be seeing like it will be fed in the coaxial feed, and they will be focused directly on the focal point of the laser, and the 3D printing is to be carried out. And once after this is done, now we have to check what are all the process in which, or like what are all the basic facilities that we are to utilize while using this additive manufacturing, or like a rep manufacturing. We need a proper high power laser, which is basically a CO2 source, or NDX source, or diode source, or fiber source. And vice versa, it comes here is like the material feeding system, wire feeder, and the powder feeder, which comes into place. And followed by CNC workstation, which is 3-axis or 5-axis. So basically what happens here is, here we will be seeing that the wire feeder and the powder feeder will be used widely to feed in the raw materials. So even the powder feeder, there are two types. One is the pre-placed bed, another is dynamic blowing. So pre-placed bed is nothing but, you might be knowing about the powder bed diffusion, where the powder is being built in the form of bed, and the layer by layer laser processing will eventually assist us in increasing the built-in 3D structures. And for dynamic blowing is nothing but the image which is shown here in this, for example, like I can mark it here. This particular one, this has the dynamic blowing, where you can see that this coaxial feed is being done using the nozzle, and it is directly fed into the focal point of the laser for melting the powder. So this is a dynamic blowing method. And we have to decide what sort of an axis workstation that we are about to work with. So this particular axis workstation may be 3-axis XYZ, or it might be like the rotational in X and Y, whereas in Z it will not be there. So that is why it comes as 5-axis workstation. And a small schematic which is shown at our right side bottom, we will be finding the laser beam and the sequential powder display, powder based deposition layer. So basic objectives, if you check here, in case of an additive manufacturing system, is like first we have to concentrate on the property of the materials. See, because here we are just taking an adequate risk where you're building a structure, and that particular component is being floated directly to the market. And of course, the quality analysis has been completely switched over. And so once after quality analysis is being switched over, like if an industry has to keep itself in the market, it has to ensure that the property of the material is meeting up with the load that the application is about to put on. Because the property varies, like building a product is something different, and nurturing that product with adequate property is a total different domain. If you check that in detail, you will be finding that the property of the material, where you have to put some concepts of material science, and that particular concept is like engineering the microstructure, and out of that, how is the mechanical property changing? And property is not something that it is just going to be sticking on with only the mechanical property, but also with the other physical properties in the aspect of tribological finishes and the precision in dimension. So all these days come into picture. So this is how the property comes into one. And the structure, as I said, when you're placing it, this particular segment structure is not just going to be a mechanical aspect, but also, manufacturing aspect, but also a design aspect comes into picture, because the structural design which is being designed will be based on certain requirements and the pre-decided properties like strength and the load bearing capacity of the product. So when we are going up with the same structure, or when we are 3D printing it, we have to ensure that whatever action we are taking, or like whatever methodology that we are deploying in the process, has to ensure that it is not compromising with the dimensional structure of the component as well. So this can be effectively tamed when we are tuning the process parameters of the entire process. So this is how we are like it has been planning to done and followed by post processing. When you say post processing here, that plays a very crucial role because uh, like uh, you can say that okay, a product is being done uh, and this particular product is having the required surface finish or not, and if that particular surface finish is not directly met uh, after for example, if that particular surface finish is not met, it is highly the duty of that particular manufacturing team or fabrication team to meet up with that surface finish, adequate surface finish that they are looking for. Because here the post processing can be bifurcated into two types. It is not just with surface finish, but also the type of stress that is being impinged on the surface. Because as we all know that the more amount of compressive stress is going to be deployed in any sort of applications, like for example, a forged product. Let us take a forged product, for example. Like in the case of a forged product, you will be finding there is adequate amount of compressive stress at the surface level and followed by the adequate amount of tensile stress or like a neutralized stress at the core level. So this adequate amount of stress in the form of compressive level or the compressive form of residual stress will assist in preventing the material from failure. That is one advantage that we will be achieving once when we are putting a lot of compressive stress on the surface of an element. And second is the surface finish. The surface finish cannot be so rugged that that is going to initiate any sort of crack propagation in the sample. So the surface finish is also a factor to be taken. And second is like the tribological property. Like for example, if the tribological property says that there has to be certain amount of surface finish on the surface, ensuring to build the next layer or ensuring that to form a better adhesive bonding between the layers in which the product is to be deployed in application, then yeah, the manufacturing team of once when you're using a 3D printing technique, you should also have that immense care that the based on the requirement you can alter the product, because this is the success of this particular process. Unless or until this is done, it is not easy to leave the shop floor. And finally, application. So this is all interrelated with each other with a detailed analysis, and each and every segment has to be met then and there. Now coming back to the raw material. So when you say raw material, the powders play a very crucial role. For example, you can see this here. Uh, you can see the several shapes of powders. Mostly, preferably, we have to go with spherical powders, ensuring that the spherical powders have a good amount of packing density. And this packing density will be very much essential and helpful when we are building any sort of uh, a component which is porosity free. If you are precisely aiming for porous components, then that is a different story. You will be concentrating on the strength and the weight ratio of the component, and that weight ratio has to be comparatively low. Then obviously you will be going for a porous structure development. And when we say this powder here, we will be finding apart from spherical, there are also some irregular shape powders and flake type powders. So these powders fabrication generally in 3D printing, they decide or the 3D printing engineers, they mostly focus on utilizing spherical powders. And also the methodology in which these powders are being fabricated also plays a very crucial role. Generally, the gas blowing powders are being used, and these gas blowing powders are being utilized in such a way that such a way that more spherical powders have been obtained from the raw material. Second point is there is also one particular drawback when it comes to a gas flowing powder. Like you will be finding that lots of gas entrapment within the powder particles are inevitable. So these are the normal constraints. And second is the particle size. It comes with layer by layer sieving. So deciding the particle size is as important as how you decide the morphology of the powder, because the particle size will decide how long the powder has to be deployed in the heat source. because when we are especially in 3D printing, when we are printing any component using a high power laser, the interaction time between the powder and the laser is very, very less. So in a short span of time before all this process is being done, we have to ensure that the right powder particle size is being chosen, so that the feeding in powders are efficiently getting deposited. Because when you say a parallel feed methodology like direct energy deposition techniques in 3D printing, you will be finding that only 60% efficient deposition takes place. Only 60% of the powder. So remaining powders, either they have to be recycled or they are going into waste if they are getting contaminated. So in order to cut short this or like to improve this percentage, you have to ensure the scanning speed and the feeding rate so perfect, or like you have to optimize it such a way that they both get along with each other and maximum deposition is possible. So this is one way of choosing the powders. So next comes the concept of alloying. So basically, when you say the concept of allowing solidification of structures, like you have the powder particles, the heat sources are impinged, and depending upon the absorption coefficient and the reflectivity of the powders, some particular percentage of that particular heat source is being obtained within the powders. And this absorption and the eventual transformation of heat along the powder particles will lead to the melting of the powders. And this particular melting process is then uh, is a point where the Marangoni effect also comes into picture and a proper melt pool is being formed here. And this melt pool has to sustain for a while in order to provide adequate nucleation process, which will be the step for the birth of microstructures. So it doesn't mean that like once a problem like fabrication is done and a proper alloying is not being done, then there is no point in going for this sort of 3D printing, and obviously you cannot expect the strength. Of course, sintering based works are also being done and they are promising in achieving certain strength. But alloying a component, mixturing with the composition, or the variety of experimentation with the composition, and as an result of that particular tailoring the composition, what is the change in the property. So these sort of games are like this sort of analysis and this sort of flexibility in engineering the nature of the component may not be available in case if we are not providing sufficient amount of heat and sufficient amount of scanning speed to be done. And once the nucleation process is started, it eventually says that the material is no more amorphous and adequate microstructure formation has initiated. Now, depending upon our requirement, just by using the same heat source, we can in fact lead or like we can in fact facilitate the growth of this microstructure. And this growth of microstructure, you will be finding that it's not just saying that you have to have a complete equiaxed microstructure based work. You can also ensure that a lot of columnar microstructures in case of creep applications can be utilized much more efficiently. So you're basically using this particular heat and you're facilitating the alteration of microstructures. So that will eventually choose the final microstructure of the product, which is going to be the first source for whatever property that we are expecting. So this is how the complete engineering the microstructure, and these are the steps that are deployed for this particular work. So the challenges, okay, now we have decided the types of AM, and now we have decided discussed about the alloying process of utilized by AM, and what are all the challenges or like what are all the barriers that is creating the hindrance for us to go ahead and achieve our goal. Loss of alloying elements. So basically loss of alloying elements is something that once when we are not homogeneously mixing the alloy, or if 2 or 3 elements are to be clubbed together to form particular alloy, the percentage and the composition of that particular alloy varies depending upon the nature of the flow and the process in which the powder goes and meets the heating source. So loss of alloying elements is also and always possible in any sort of additive manufacturing technique, and followed by porosity and fusion, because there might be certain elements which are highly sensitive to oxidation in the surface atmosphere, and these oxidation gases like oxide gases are get themselves entrapped within the solid structures, eventually leading in space and void, which might pull down the quality of the product, and followed by, once after this uh, alloying is done or the porosity, everything is like attained as per the requirement, the next challenge will be the surface roughness, as I said. Because at one point of time, when there is too much of surface roughness, then eventually the crack propagation point starts at that particular level itself. And as I said, eventually, like if we are not addressing this issue, lots and lots of surface cracks and delamination effect happens during the alloying process. And also, since there is a layer by layer, like the laser tracks are frequently induced or impinged on the deposited layers, you will be finding the accumulation, rich accumulation of residual stress happens in the alloying element. So here, this is the conventional DED technique, like a laser additive manufacturing technique, where parallel feed powders are being utilized. It is passed through the hopper. Like you can see the image in the top left, where you will be initiating with a dual powder feeder. So basically, this dual powder feeder is nothing but it just facilitates the alloying of the final product either in the form of two pure powders. In other ways of doing this is you can also go for a pre-mixing process. So the pre-mixing process is basically nothing but you have to alloy them using ball milling or any sort of tabletop pre-mixer, and the powders are to be pre-alloyed before feeding into the hopper. And once after this feeding process is done, like once you pour it into the hopper, you will be finding that the argon gas will be gushing through the hopper. And this argon gas, which is gushing through the hopper, is nothing, not only just acting as a carrier gas, but also once when you shift the powders from the hopper towards the deposition booth, any chance of contamination and any chance of oxide formation of the powders will also be efficiently prevented. So this is how the process is initiated, and the powders are fed through the tentacles which are shown here in the video, which is clearly seen, the metal tentacles. So these tentacles are directly connected with the powder feeder, and the argon gas which I said, which is going to be acting as a carrier gas as well as the noble gas too, which creates a controlled atmosphere. So basically argon is chosen for widely rather than helium, unless or until there is some certain specific application due to it. Generally argon is preferred. Argon assists us in maintaining or sustaining the arc that is getting generated at the focal point. So preferably, mostly argon gases are widely used. And second, the argon gas has proved itself to be much more efficient in preventing any sort of presence of moisture in the deposition booth. So this is why precisely argon gas is being widely used here. And so they are acting as a carrier gas, they are gushing in. So it's an automated process from the dual powder feeder. It is just gushing directly to the deposition booth. And we know that the laser head, which is being utilized for this particular deposition, you will be finding that this laser head will be fixed into a normal 5-axis manipulator. And this 5-axis stage manipulator will facilitate, like in the top XYZ is being easily done, and at the bottom X and Y, which is being controlled by using the controller. So all these 5-axis workstation which is shown, which is inside the deposition booth, will be controlled by the Siemens based controller, which is kept here, operator console. So here it is not just controlling the operation of this XYZ stage of the deposition head. Also, it will be the interface through which the programming can be entered for functioning. You like the proper programming which has to be entered for fabricating the structures layer by layer will be assisted by this Siemens based controller. And you have a 2 kilowatt fiber laser based source. You have a 2 kilowatt fiber laser source, and you can see that the system is kept thoroughly outside the deposition booth. So basically, the power is so high that they cannot afford any sort of risk within the deposition booth. At times it can create any type of chaos which may eventually lead to trouble in fabricating the components. So now as a result of this particular option, like now we have to bring the laser in the from the source towards inside the deposition room. So for that particular process, we use fiber optic cables where efficiently without any much of loss or like without almost like negligible amount of loss, the transformation of the laser energy will be brought inside the deposition room. Okay, so this is one of the best indigenously manufactured systems in India. It is with Dr. C.P. Paul from Lab, Laser Additive Manufacturing Lab in RRK. And the advantages. So what are all the advantages that we are getting out of here? Like as I initially said, it is a novel method of developing and the composition study can be varied, and also complex geometry fabrication is quite easy compared to the conventional fabrication techniques. So that is one way of looking at, and in fact this really motivates to bring out lots of complex geometry structures that can be easily built without much of error or much flaws. And even though if there is any birth of errors in the component, then and there they can be rectified using this particular technique. And the entire fabrication of complex geometry has been very much easified by the invention of additive manufacturing. So this is the pros of the process. And as I said, any process will also have certain restrictions from utilizing it completely, is where due to the time, the laser interaction time with the powder is comparatively very less, you will be finding one surprising factor that the brittleness like certain materials like titanium based work, aluminum based work, nickel based work, what happens is it induces a type of brittleness. That's because the lesser time of laser source which is available for impingement will give birth to the formation of lot of dendrical microstructures, which eventually leads to brittleness. And as brittleness comes into picture, obviously it will be followed by low and medium strength. And all these effects will be due to the effect of high residual stress on the surface. And solution is we have to go for a type of laser processing technique like laser sharpening technique or laser annealing technique, depending upon the application and the utilization of the final output. So based on that, you have to like decide what are all the parameters that you are about to use and how an efficient deposition can be carried out. So I would say that if you have any doubts, any participants, so please stop me then and there and you are free to ask. Please feel free. But rather than just thinking this as a talk, you please consider this to be a type of discussion. Is that fine, sir?
Yes, sir. It is okay.
Yeah, so please feel free to have any sort of discussion and any sort of clarification that you will be requiring in this entire process which I am discussing. Clear? So
Okay,
yeah, this is the second type of additive manufacturing which has taken the world by storm. Like this is wire arc additive manufacturing. So you can see this here. This particular setup is currently like this is one setup which I had utilized during my postdoc at IIT Madras, the Department of MEME. So there you will be finding that you use a type of CMT based source, a cold metal transfer source. And this CMT based source is now utilized. It is connected with an XYZ stage. And this really assists us in building the 3D structures. So here this computer controlled ignition and the welding touch process is going on. And you will be finding that you can see the tracks which are built at the bottom. So for the various parameters, what are all the nature of the tracks that is being deposited, and as an effect of that, next step is like we can decide the flowability of this molten material, because depending upon the flowability, we have to decide what is the pattern of deposition that plays a very crucial role. And this is not just for wire based additive manufacturing but also for your powder based additive manufacturing. You have to analyze the chosen process parameters and their corresponding output, where you have to see whether if there is the track is going to be homogeneously long, or the thickness and the width of the track is being maintained homogeneously throughout, and if they are done so, like how long it is being carried out, and is there any necking process, and if so, how come that is going to assist in the overlapping of layer by layers. So these are the crucial parameters that one has to decide before stepping in for building the structures. Now you can see to the right bottom, you will be finding a 3D structure. It is nothing but a type of NITA structure, wall structure, which has been fabricated using the same technique. And along with those actually fabricated image, you will be finding the results of XCT, X-ray computer tomography. So basically the XCT results show very clearly that the built-in structure is almost like 99.9% porosity free. And the corresponding proofs are like it is shown, like when you see, once when you see the XCT results, they are like several slices throughout the length of the product. So this in fact assists us in realizing or like rectifying the uh, errors in that particular processing parameter. And if we find any sort of errors in the like in the form of porosity or like any sort of void formation that is frequently coming into picture, then immediately it is an indication for us to change the process parameters and retry the experiment. So these are the basic NDT techniques. So once the parameters are optimized, then we can go for fully fledged construction process of the final product. Now, this is the third type where this is very novel and very much new nowadays, where spraying techniques, like basically when you say spraying technique, you will be finding that they are widely used for coating. As mechanical engineers, you will be knowing that lots and lots of coating works, which is to counter wear, which is to counter corrosion, or like to improve the strength on the surface, a diffusion based coating. For this particular process, a spraying technique, like if you are to engineer the surface, like a surface engineering process is to be done, then the respective spraying techniques are used. And what are the spraying techniques? You will be having a flame spray, HVF, and detonation gun. So these are the combustion based spraying techniques. Followed by here we have arc spray, atmospheric plasma spray, vapors plasma spray, and LPPS, where you will be having electrical based deposition. So the arc generation is thoroughly dependent on an electrical process. Like for example, you need to have proper current and you need to bring the proper polarity between the
Excuse me,
electrons.
sir.
Yes.
Excuse me, sir.
Yes. Yes.
Sir, I have a doubt. Sir,
Yeah,
in the
please.
previous method that you said, the wedding method, sir, you said it is 3D printing layer by layer. So,
Yes.
sir, after the layering,
Yes.
sir, whatever the output we are getting, then we have to shape it to
Huh,
get the desired
yeah.
product.
That is what I'm saying is like we have to check the flowability. Like for example, you can see the slide which I'm showing you down here. Like for if you can see this tracks which are getting developed, like can you see the encircling which I'm doing?
Yes, sir. Yes, sir.
These are the tracks for each and every metal. So these tracks are just checked or they have to be optimized with various processing parameters. Like for example, in case of wire and additive manufacturing, you can alter the voltage and current of that sample of the machine before the input is being done. So you have to design an experiment step by step for a particular material to check which gives the best of the deposition. And once after the deposition is done, now you can see the image at the right bottom. We have developed a wall structure and layer by layer. Now, if I feel that this chunk is good enough to serve my application, it is just like an inserting plate or like insert fitting that I have to use, then we can obviously go ahead with the as built structures. So if my application demands a proper surface finish without any sort of rugged formation, then we have to go for a kind of post-processing techniques. Like you can use a normal surface milling, surface grinding, surface buffing. So these are the options which are you're getting additionally to nurture the product that is being built here. It is not compulsory that you have to go for post-processing, but if your application demands, yes, we are also having the opportunity of utilizing these post-processing techniques to achieve our output.
Okay, sir. And
Sir?
sir, one more
Yeah.
question. Sir,
Yes, please.
what is the material used?
Material, yes, this is a very good question. Like for example, my area of research, as I said in initially, that I work actively on functional materials. These structures are nothing but shape memory alloys. NITI, nickel titanium nitinol, for these applications. And similarly, you can use it for any material, either be titanium, nickel, soft materials like copper, aluminum. So depending upon any sort of wires that you are using, you are free to deposit any material. You like this is the biggest advantage of 3D printing technique, is that you need not constrain yourself with any sort of a restriction that only this so and so material can be deposited. No, even metals, non-metals, everything can be achieved, and that is giving successful results. Have I answered you, sir?
Sir. So, sir, for biological process also, so,
Yes.
sir, we had one thing coming up recently that uh, biological organs can be printed. So, with
Yes, yes.
biological
In
cells.
fact, in RRCAT, when I was pursuing my PhD, we also worked in one such project where the hip bones implants, they are basically called as human implants, were also 3D printed using bio-friendly metals. Like there are certain titaniums or like titanium oxide-based powders where they are bio-friendly, and your body in fact accepts it and allows the presence of such materials within your body. So that particular element, or like that particular, and also now very recently you will be finding one more thing, biodegradable implants, where at one point of time when
Yes, sir.
you fix it, eventually they get degraded and that gets digested. Mostly zinc based, zinc oxide based works. That is also being frequently done, and that can also be printed. That is where it is widely used. Like for example, you can take your dental implants. Each and every one will have a difference. The teeth size is not a constant template. It is going to vary from person to person. So for each and every person to person, rather than just manufacturing a die and going for a conventional manufacturing technique where that is going to lead in much more overhead cost, that can be efficiently done using 3D printing with a very with a one time investment, rather than just going for an like each and every time depending upon the customer requirements. So that customization option is also very well much more versatile in case of 3D printing comparing to a conventional manufacturing process.
Thank you, sir.
Thank you. Thank you.
Sir,
Yes.
excuse me.
Yes, sir.
Sir, I think this wire-based 3D printing method is more suitable for the material for which we cannot convert it into powder.
No, sir, it is not like that. See, actually, there are two things we can see this here. I will tell you when you see this particular metal. Sorry, one second. In this powder-based technique, either direct energy deposition or SLM, what happens is that there are certain element, and our requirement is in such a way that, like the previous participant asked, if you need to build in implants, implants are widely made with porous structures with adequate strength and light weight, because when you're pushing an implant inside your body, that doesn't mean that the hand should always cope up with the weight of the body. So we are forced to build porous structured implants as well to meet up the application. So when you need to build with porous structures, laser based applications or laser based deposition technique are much more efficient, and they are much more easy to fabricate the porous structures. Whereas when you see this wire based one, they are widely used for bulk structures. Like for example, like if an object has to be deployed, like when you are going to replace this an object which is being conventionally manufactured and forged, and if you are looking for some sort of replacement in that particular angle, there you need high almost like zero porosity should be tolerated. You cannot tolerate much porosity, because once when the load is going to act, that itself will initiate the failure. So to prevent that, when we are going for building bulk structures, we can obviously go for this wire-based additive manufacturing technique. And second point, like you said, the raw materials, the green manufacturing. Slowly, the world is moving towards green manufacturing. So in green manufacturing, wastage should be less. Maximum utilization of raw materials are motivated. So in this particular objective, wire-based works are much more efficient than the powder-based works. So these are the flexible options. It's like buffet. It's up to you for our application, which one we are going to opt for.
Well, actually, in this wire-based technique, the material is deposited by a welding technique, I think.
Welding source is used. It is not precisely welding. See, when you say welding, there is this is a good question. So basically, what is the difference between welding and this 3D printing? That's what you're asking. Am I right?
Yes, sir.
Yeah, basically when you say welding, welding is widely used as a type of joining technique. where you'll be having a base material and then you are going for a type of bridging. It is basically limited to say that it is a joining technique. But using the same source and building a 3D structure wall by wall independently XYZ direction as per our requirement, then that is where the 3D printing comes. And second, you may ask, then what is the difference between an automated welding and this 3D printing? So in that case, what happens is in an automated welding, it is very much restricted within the material where the welding is to be done. A type of the joining technique, like for example, we are going to weld a pipe or weld a plate. We are just ensuring and nurturing that joint to be efficient with the parent material. So it is just a joining technique is where this welding is being used. So that can be precisely done even manually. That is why we have lots of welders in action. But when you say additive manufacturing, what happens is the precision in each track has to be sequentially repeated. Only then you will be able to get a good structure. If the repeatability is lost and if there is an error in manual work to be done, or if there is any manual flaw in the deposition speed, and if there is any fatigue error which happens which goes beyond the precision in the manufacturing, then that will not be considered as a proper 3D printing technique. Their precision cannot be compromised. So that is why this has been automated using this manipulator.
Sir, one more thing. When
Yes,
this
sir.
wire is coming from the nozzle and touching with
Yes,
the substrate and it producing arc, and due to that arc, that wire is melting or some other method is used?
In CMT, you are asking, sir?
No, sorry, in this wire-based printing.
No, in wire-based printing, now we have, that is a two different the issue. I'll tell you, like you said, the conventional welding, once the electrode will come, it will touch the anode and it will be cathodic joint. And once
Yes.
touched, due to the thermoionic reaction, the arc gets ignited and the surrounding gas will just ensure and maintain sustain the arc for a while so that you have adequate time to melt the electrode. Am I right? This is a conventional welding
Yes.
process. So when you say this in case of 3D printing, what happens is like in this particular technique, CMT based technique, what happens in the conventional welding MIG or TIG is like what we had discussed, you cannot control the heat generation or you cannot control the excess amount of heat because the moment the arc ignites and it is sustaining for a while, the temperature will be shooting up, even it can melt tungsten. So it will go beyond 2800 to 3000 degrees Celsius. So this enormous amount of heat wastage can be restricted using this cold metal transfer. In cold metal transfer, what happens is the moment the arc gets generated, there will be a short circuit that is induced and the arc will be almost extinguished. And as an effect of that extinguishing arc, excess amount of heat formation can be controlled. And once when you control the excess amount of heat formation in the deposition, obviously this unwanted heat is away from the melt pool. And if this unwanted heat is available, it induces a type of secondary phase formation in the alloy. And in case of cold metal CMT based cold metal transfer based source, this problem of formation of secondary phase alloys will be prevented, eventually avoiding brittle phase and porosity formation within the alloy. This is the magic behind the bulk deposition to happen successfully.
Yes, sir. That means in CMT machine, sir, that wire is passing through that arc.
Yes, wire is actually passing through the arc and that wire will be pulled back for that, like it is a push-pull technique basically. The wire will be pulled back so that the arc, the droplet gets itself detached and the droplet will be falling in the melt pool to get solidified. So that is how the detachment process is also done. And the biggest success of CMT based work is like you will not have the electromagnetic force which generates due to the Lorentz force in conventional welding. And that absence of electromagnetic force will prevent a large amount of spark formation, like it will prevent spark formation. So
Yes,
this
yes,
is also one big advantage in case of CMT based work where it can cut short the heat because too much of spatter formation will eventually lead to surface porosity and heat distribution. That can also be neglected using this CMT based technique.
okay. Thank you, sir.
Rahul sir? Yeah, sure.
Yeah, yes, sir.
So yeah, going ahead, we will be finding the spraying technique. This is a new novel method which is fascinating many users. Like spraying, as I said, this is widely used for surface modification in the aspect of coating. and lots and lots of coating is being done, and this coating techniques is just to alter the surface level of the product efficiently for to be corrosion resistance, wear resistance, and to improve the strength, like diffusion based coating like plasma nitriding is being done. So now this coating technique is what is new in market, where it can be efficiently used for 3D printing components as well, and that is where is this cold spray based one, like you will be seeing wire spray, cold spray, and HPF. You can see this here, like this is the nominal, this is a sketch which shows a cold spray based work. In cold spray based work, it is very simple. The entire operation is successful in fabricating high dense components and this thickened substances by the D level nozzle. You see this particular nozzle here, right? You can see this here, this particular segment which I'm encircling now. This is called as D level nozzle. So this D level nozzle is one equipment that creates the entire magic. So what is this D-level nozzle? How it functions is, it is nothing but it is just a compression and expansion nozzle, a normal compression and expansion nozzle. But you will be really surprised to know that this small compression and expansion nozzle is creating such huge magic which other conventional manufacturing techniques are not able to meet up with. If you check what is that, you will see the diagram on the uppermost left topmost, that is a schematic where the powder is being fed. You have a compressed heated air and there is a chamber, and as it passes through the nozzle, the entire heated air is more compressed, and as the compression is done, when they are passing through the expansion phase, there will be a sudden expansion where all the absorbed energy will be ejecting out in high speed. Eventually that high speed, that is where the kinetic velocity gets generated, and when you feed in powder at that particular point into the nozzle, the expanding high speed will the expanding high kinetic energy will accelerate the powders to move forward with high velocity. For example, you won't be imagining the speed of the powder that is getting out of the nozzle will be somewhere around 2.1 max speed. So 2.1 max speed is, you can imagine, 2800 kilometers per hour. So if you create such 2.1 max speed in that output, so what happens? All these powders, if you have the substrate, you will be seeing that they just start getting impinging themselves one layer by layer. So beyond the coating technique, this is where a bulk fabrication, a bulk product fabrication can be much efficiently used. So that is where the deposition of bulk samples can be much more efficiently done, and that particular bulk deposition is nothing but it is just a layer by layer impingement of powders. So there is one small difference in cold spray technique. A proper alloying is not taking place within the impingement, but rather you will be finding that the impingement rather than alloying is formed with the powders. A type of impingement is being formed on the surface of the powder. So all the 3D structures which is being formed here is nothing but it is just the impingement of the alloys that is being injected in. So our objective is not just to impinge the powders. We have to create an alloy. Unless or until we don't create an alloy here, you are not going to have the material property that you are looking for. You get the point. So this particular technique is something that where you will be utilizing it for a further heat treatment process. Like this is a natural setup. This particular setup is at Institute for Manufacturing at University of Cambridge, where I was working as a visiting scholar during my PhD days. So this is an indigenously developed setup where they use the nitrogen gas as for the initial gas, which is being connected directly to the mount, hopper mount, where the powders are fed. And eventually, as this hopper mount is fed, you can see this, it falls into the deposition booth. Again, similar tentacles are being used. And you have a gas preheater, which is completely computer controlled. And this particular gas preheater will heat the powders. And this heated powders will be assisting in deposition of tracks. And you can see the final track which is getting deposited. And when we check this particular white segment, like this particular white segment here, you can see how the structures happen. Like you see the schematic functioning here. Like you have the nozzle and you see this black color input where the powders are efficiently fed in. And as the nitrogen gas heats the powders, you see the expansion to be taking place in a much more efficient way. And as this expansion prolongs here, you will be finding that the efficient track deposition is taking place layer by layer. So this is the schematic diagram of the D-level nozzle which is being used. So it is basically a convergent type where the powder mixed hot particles are compressed with nitrogen gas and fed along the converged side of the nozzle. And as they pass through the throat, that is the point where you will be finding that the maximum amount of compression that can be burned up by the gas is being fed into the throat. And immediately after the throat, you find the divergent section where the actual acceleration of particles, that is the expansion of the gas, nitrogen gas, generates the kinetic energy, and that particular kinetic energy gets drifted on the powder particles, and that acceleration eventually assists in impinging and coming out in that high speed. You can see. So this is what again and again I'm saying that the high speed at 2.1 Mach. So that is the point where actual success lies. Like unless if you are not meeting that maximum speed, the impingement of powder is not going to be as easy as it is shown here. So to have that much more efficiently, or like that impingement to be done much more efficiently, you have to ensure that the stand of distance between the nozzle and the substrate should be in an optimized way. Because if you are moving the substrate plate randomly away from the nozzle, you can see the amount of track that is being done. The short, like you can see the deposition efficiency for a short stand of distance, that will have the low deposition efficiency. And as this prolongs here, you see the optimal standoff is between these two. And the last one is also again the low, the longest. The reason being is very simple. The dilution of the generated kinetic energy. If it is more here in the front, if you see this first statement, like in this particular positioning, you will be finding that it shows low deposition efficiency. Why is that happening? Because tremendous amount of speed is hitting the surface, and as these powders are highly charged up and they are having a high kinetic velocity here, what will happen is at times the powder particles, if they are very large, if they are not optimized between 10 to 50 microns, anything more than that, what will happen is they will hit the surface, and two things can happen. Either they just hit the surface and revert back, proper impingement, the first layer impingement does not take place at all so easily, or the other way around, the powder particles themselves start breaking. And if the powder particles start breaking, eventually you cannot expect the material property that you would like to have. So this is the difference. So if the powder particle starts breaking, then obviously you will be like left out with no option that adequate, like the required material property will not be met out. And when we come to the next level, this particular distance, yes, there is no bowing effect. This reverting back or this rebounding back effect is called as bowing effect in cold spray. And if there is not much bowing effect taking place and the impingement is sequentially hitting on the surface, so what happens is maximum deposition, like almost 99.9%, just like your wire. This is one of a primary setup where the maximum deposition efficiency will be achieved. And next level it comes is the substrate. The substrate, what happens here, like as this impingement is being done and it is with a low efficiency, what happens here? As the kinetic energy slowly, as the distance keeps on increasing, this will be the powders will start slowly drifting away from the absorbed energy, because once when you observe this kinetic velocity from the expansion, and they last in that excited state only for certain limit. After that, the absorbed one will start drifting away from the deposition track. So as an effect of that, the impingement will not take much more efficiently as how you would like to have. So the deposition efficiency gradually falls. So this is the reason between three different layers, that this is an importance how the standoff distance has to be efficiently chosen for high deposition efficiency. And second point, it is not just the standoff distance. When you see at the bottom here in this particular segment, you will be finding that the angle of spray, because when you see, when you keep it in 90-degree deposition, and if you start building the tracks, you can see the nature of the tracks. It is somewhat almost like a bun-shaped structure. You can see this here. So basically, when you have this bun-shaped structure, what happens? This bun-shaped semicircular structure is not much friendly to generate overlapping layers, because the success of additive manufacturing is there has to be an efficient overlapping process that has to be taken into picture. And if this overlap is not as good as how you would like to have, then that itself will be the site for void formation. So the width aspect ratio of the track, they generally used to say, the width and the height of the track should be in such a way that the overlapping is much more efficient. Once when we tilt this gun to 45 degrees, you find this here. What do we hear? The structure of the track is somewhat like a meniscus structure here, upper meniscus structure here. Clear? And that particular upper meniscus structure is basically formed, and that is much more efficient in which assists much more overlapping more efficiently without formation of any sort of voids or delamination from the substrate. So these are the advantages. So it is not just the standoff distance, but also you have to optimize the positioning of the gun for each and every powder depending upon the output. So here we find next is the third one, the in this region, like when we see the right bottommost, there is also one more factor you will be finding is like the oxide layer formation. The powders that you are feeding into the nozzle are subjected to heat and nitrogen. It is not just oxide. At times what happens is there are also formation of nitrates, because you are using nitrogen here, and that forms a thin layer around the powder particle. And this particular thin layer of nitrates will start exposing themselves on the surface, and you will be finding that they are breaking, and that impingement is not sufficiently taking place due to the presence of this yellow layer. So the oxide layer or the nitride layer that is enveloping the powder particles have to break in the speed that they are traveling through and hitting. If they don't break, the material jetting and this melting impingement along the surface will never happen. They create a type of loose bond as it is shown here, and that will eventually lead to disembarment of the impinged powder particles. So these are the primary cautions that has to be taken in an efficient deposition process. So the next one comes like here. You see that the blended powders, satellite powders, and as I said, the Boeing effect. You see this here, like a release of substrate. The substrate is being kept and you're impinging powder particles with high speed. And what happens here? The residual stress formed in inward curvature and formed like a outward curvature. It can just bulge on the top or bulge at the bottom. So this thoroughly depends upon the heating temperature of the powders, and also the speed of the powders that you are looking for. So generally, which is preferred is like once when we have this bending effect at the bottom. If the bending effect happens much more at the bottom direction towards top, that will, excuse me, excuse me. So that will prevent any sort of curvature, and a smooth, proper process will be taking place throughout the deposition of this cold spray. You can see the tracks here as it is shown here, like with various angles, the number of tracks that is being deposited and their dimension. You can see this here. The dimension is such a way that they are almost very sharp by nature. You can see this. If 20 mm per second based deposition, you find it here, find this one. The peak is very, very sharp here, like almost like a perfect triangle. So if you have this like this, the biggest drawback you will be getting is you will not be having the sufficient overlapping to be successfully done. So what happens here? You have to ensure that this sort of meniscus based, this is happening as low as possible for efficient track deposition. And that is where the speed of the powder, like you can see 200 mm per second is taking place. Now next comes is the angle of degree, inclination. So when we have a proper angle of inclination, how the meniscus formation is supported. All this is also a type of optimization which is being done, and this can be done on either way. And you can see the image at the bottom here. It is an as fabricated component, and you desire to have these two extra machined attachments here. So how do we do this? Like when we say that when we have sharpened edges like this, so what we do is we build the actual structure, and we have to build some extra more deformed structure, so that by further post machining process, that will be assisting us to remove that undesired section with the deformed shape, and the actual shape can be easily obtained. Clear? And this particular desired part, this doesn't mean that, okay, sir, I have just fabricated this, now I'm going to utilize it in the application. If you are going to do that, obviously you will be having a biggest disappointment, because the object will not function, because there is no alloying at all taking place here. What has happened? It is just the impingement of powder that has been efficiently taken. Now you have to alloy this. So for that particular job is where you have to go for a post heatment technique. Like you take this desired part job and you put it in a furnace and allow them enough sufficient time for melting to take place. So once when they start melting to that particular level, you will be finding that a proper alloy formation is sufficiently taken place. Clear? Yes or no, sir? Anyone?
Yes, sir.
Yes, fine. Thank you. So yeah, this is how basically the alloying process is done. Now, one more technique which is much more novel, and that is also being approached by several users in the market. That is nothing but you will be finding your people have started using lasers for sufficient utilization, like the surface level melting. If you have a requirement that sir, at the core I need not worry about the melting process to be done successfully, I am just looking for the surface level melting so that the object will be good enough to bear up the load. If something like this particular condition comes into picture, then you have to figure out that this surface level melting can be efficiently done using a what do you call this sort of laser based localized heating techniques. So the alloying is not restricted just to use a furnace, but also to use this laser based non-conventional beams, laser beams, actuated electron beams. All these are the other way around for utilizing the or like alloying the element in much more efficient way. And next comes is the pattern of deposition. So the pattern of deposition can be bifurcated. This is very common for all types of additive manufacturing techniques, either be your cold spray based technique or your laser based technique. You will be finding that these techniques are much more like unilateral deposition and bilateral deposition. So this unilateral and bilateral deposition basically just justifies how the like in other words to say what sort of amount of residual stress that each and every track deposition has, because the track deposition is something that you will be finding uh, that thoroughly depends upon the amount of residual stress, because you cannot allow too much of residual stress to get accumulated between each and every track, because that itself will motivate the debonding within the tracks. So in order to avoid this, you will have to ensure that the track opposition, like the deposition that you are opting for, is going to be unilamellar or bilamellar based deposition, and that particular cross section has also to be analyzed so that efficient deposition can be taken place. When you come to this cross hatching B option, which is being shown here, you can see the first layer to be a bilamellar deposition, and you can see the second layer, the same bilamellar deposition, but the pattern is different. So all these attempts are basically done just to ensure that the deposition which has been done is done without any sort of porosity or void formation, but with high packing density. So these are the ways in which you can counter the or like maintain the density, high density within the object. So coming back to the nozzles, the D-level nozzles are not just convergent and divergent nozzles. The same nozzles can be utilized in different way depending upon the speed and the utilization. You can see it is not a divergent part which is shown in B, which is quite similar to ours, which I have shown in the previous slides. Whereas similarly, you can also have a straight impingement where high expansion is not required and even low max speed can impinge the powders. This can be used for soft materials, and also the C1, you can see the same soft materials like aluminum, copper can be efficiently deposited using this sort of nozzles. And the thing is like a difference between A and C is in A, the track dimension is going to be small, and C, the track dimension is going to be large. So this is the difference between the types of D-level nozzles that are used for spraying guns in the process. And these process parameters, these are the widely used process parameters in and around in coal spray for efficient deposition to take place. So this comes in case of industrial application. See, all these applications here which are used, you can see that these are all higher end applications which takes lots and lots of painstaking efforts to fabricate. And also you can see this propeller and this camouflage flicking compressor drive which is shown here, and also most importantly the right side top image which shows the gun liner. All these applications are something that we cannot give any sort of error. Like the percentage of error which can be allowed is very, very less, because the precision should be so high that it does not harm the user. Because in all these sort of applications, if you are compromising any error and proceeding ahead, what will happen? In case of a gun liner, at times if the gun liner, once the shooter fires and the gun blasts here and this bulging effect takes place in the gun liner, eventually that bullet will go off the target and he is not going to be successful in his particular target. So you cannot compromise in any way, or even a little bit cannot be compromised in the output application in this particular examples which I have chosen. So what eventually happens here is, in order to maintain that factor of safety at higher level, we have to ensure that like for example, let us say a gun liner is fabricated using conventional casting process. It has been put up in certain application, and as it has been frequently utilized in application, it has worn out. Let us assume a case like this. Now simply if it is worn out, we cannot throw it out in the dustbin and discard it, because already investment is huge in this, and much more efficient, much more efforts have been put for fabrication. Now, if you need any sort of technique that can efficiently repair the faults in these sort of equipments, that is going to be additive manufacturing technique. So, depending upon the nature of the job, you can decide whether to opt for cold spray, whether you are going to opt for wire-based works, or you are going to opt for a powder-based work. So, these are the several types where you can make hollow tubes using cold sprays techniques as well, where you have a mandrel which can be deposited, and over the mandrel you will have the cold spray to spray the nozzle, and this particular mandrel will be rotating by nature. So after deposition, you see the green color one, that is the deposited element, and now within that deposited element you have to etch out the mandrel which has been done, which is basically, preferably, that is why these mandrels are kept as in the form of polymers, so that once you etch them off, what happens here, that residue will be this powerful, or like this remaining hollow pipes. So this is one way of fabricating hollow pipes using cold spray technique. And similarly, the same cold spray technique, when we need to induce more compressive stress on the surface, you are extra attaching some sort of roller based works which can efficiently induce the required compressive stress on the sprayed powders, and that will eventually help in restoring the compressive stress on the surface to counter failure. So this is one way of doing it. And similarly here, building structures using a lathe based head check, where the component is fixed and you have the spray gun at 180 degree, at 90 degree, and the entire setup functions at 180 degree. And this, even though if it is at 180 degree, we will be finding that the enormous pressure that is being impinged through the nozzle will not allow the wastage of powders to take place. Now you can see the various tracks, like you have a type of titanium deposition on aluminum, because joining titanium aluminum in manufacturing is one of the most tedious tasks due to their respective nature. But what happens here, when you cold spray them, the sandwiching happens very, very easily, and the alloying also happens much more easily when they are previously cold sprayed and the shape has been maintained throughout. So this is also a much more efficient way in fabricating and creating dissimilar joints among the samples which is being fabricated. And these are the structures which are used for heat exchangers, and this pyramid fins and trapezoidal films. And these fins are used in the as integral part of heat exchangers, and they are so small. And here you will be finding that the pyramid fins, when they are frequently being used, they become the trapezoidal fins. And now to repair them, and if the pyramid structure is to be restored, then obviously we can go for this sort of cold spray techniques to get the job done easily. Apart from this, yes.
Sir, what is the temperature required, like temperature that is to be achieved?
The temperature here is, like, for example, if you're depositing an element like titanium, nickel, then you will have to maintain a preheating gas temperature at around 450 to 500 degrees Celsius. At times, even 700 degrees Celsius has proved to be having the best of the depositions. And if you are dealing with low melting element like aluminum or like brass, tin, or at times even copper is having good, it is more than 1000. Like aluminum, brass, tin, these sort of applications, then comparatively you can do the job at the 400 degrees Celsius, 500 degrees Celsius temperature as well. So that only thing we have to ensure is once when you are depositing here using the deposition gun, you have the D-level nozzle, which I said here. When you are using the gas, we have to ensure that these powder particles are completely melting and they are getting themselves exhausted out of the gun like this. Because if we are allowing an improper heating here, what will happen? The powders will start to clog inside the inner side of the nozzles like this, and that will not allow the free flow of powder. This sort of clogging effects will take place. So we have to ensure that the gas temperature that we are choosing is it's not only melting the powder, but also the transformation from one point to another should happen very smoothly and swiftly. Have I answered, sir?
Yes, sir. Thank you, sir.
Thank you. Yeah, so the space and aerospace applications are widely used. You can see this sort of propeller nozzles which are used for space applications, which are completely manufactured using cold spray. Tool mold making. For in casting, you have to make a lot of mold, and those mold making machines are also being done using cold spray based additive manufacturing. Then in defense application, this cold spray based additive manufacturing has been successfully utilized for making drones. And these drone structures are also used for defense application in surveillance based works, and are used as permanent magnets. So these magnetic structures are used as used to chuck two parts much more efficiently when it compares to the normal coupling which is being used for joining the pipes. So this permanent magnetic materials are also much more efficiently 3D fabricated, 3D printed using the cold spray based techniques. So this is one such work which I would like to show. This is the shape memory alloy based work which I had carried out during as part of my research. It is all a functional material which is widely used for functional applications. You can see this actuation on the application of heat, the actuation takes place. The material remembers the shape of U and it just returns to the shape. So this sort of application for bulk applications, like you can also use the shape memory alloys for smart tool holders, where you apply heat. What happens? It just starts to clamp the tool even more tightly. And as an effect of that clamping the tool much more tightly, we will be finding that there is less vibration taking place, and also the heat generation in the neck, in the tip of the sample due to vibration can be substantially reduced, and the life of the sample can be increased. So these are the works that were done part of my research, and these are also like a shape memory alloys which were developed using a compressive like a cold spray based work. And from this, the conclusion part, coming to the conclusion part, I would say that the cold spray is also, and like it is just an awareness where you can widely be using that to be a good 3D printing technique or like a good additive manufacturing technique. Development of standards across all the types of additive manufacturing is being actively done across the world. So that is one particular area of research which can be well explored. And eventually, like developing the standards will in fact help us to counter the current challenges we are facing, like brittleness and overheating and this void formation and any sort of defects like porosity and crack formation. All this can be prevented once the standards are formed, and hence, if the standards are successfully developed and if we are countering all the problems that the challenges we are facing in an efficient way, there will be error-free components that are getting fabricated much more frequently. And as a result of that, the reliability of additive manufacturing in real-time application will be much more effective in case of your application point of view. So that is why we are much focused in developing standards and development. So when you say additive manufacturing, this is our research lab, this is my research lab at IIT Jammu, Laboratory for Advanced Manufacturing and Processing. So here we are soon about to have an additive manufacturing setup, a 2 kilowatt fiber laser based indigenously developed system where you can 3D print components, metal, it is used for only for metals, and also a cladding head where using a chuck for joining applications, the same system can be used. And similarly, a wire arc additive, CMT based wire arc additive manufacturing system, and also the same additive manufacturing system which we use the laser source will also have a wire feeder to efficiently deposit the tracks. So one machine can just do 3 different roles, that is how we have locally customized these machines. And apart from that, we use high power pulsed lasers for laser post-processing techniques like laser annealing and laser shock peening, where conventional compressive stress inducing techniques are not much of successful. We generally use this sort of techniques for countering the efforts. So currently we are handling projects from ISRO, DRDO and DSIR. So in ISRO, we are working on high temperature, high entropy alloys fabrication using atmospheric plasma spray. And also we use high power lasers for laser surface processing to postpone failures in nickel superalloys. And in DRDO, we are using this additive manufacturing technique for fabricating certain mechanical components for their defense applications. And from DSIR, we do have a project where we are developing standards for manufacturing components out of stainless steel for high temperature application and defense application. So these are the various projects that national projects that we are carrying out in our lab. So currently we are having a strength of 3 PhD scholars and 2 JRLs. So as projects come more and this much more activities have been carried out, you can feel free to collaborate with us at any point of time. And so thank you for the patient timing and for patiently listening to my talk. I hope I kept up with the time. I think Professor Das can say.
Yes, sir. Yes, sir. Thank you, sir, for such a wonderful session, and it was quite interactive.
Thank you,
Any
sir.
questions? We would like to take a few questions, if any.
Sir, I have one question.
Yes,
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 sir.
please.
Sir, you said that one spraying technique, we are using mandrel to make a hollow tube like that structure. So,
Yes.
what should be the property of that hollow mandrel?
It should
Means,
actually
what kind
be
of
some
mandrel they
sort
can
of
use?
that mantle should actually be some sort of degradable. It should be degradable polymers or composite types where they can be dissolved using alkaline acids. So that particular part will be assisting us to remove this mantle. Like you will be having the mantle as a base, and the mantle will be rotating. We will be developing springs and this hollow tubes on the surface efficiently. And once after the development is completely done, you can just take that sandwiched component, that output, and you can put it in that acid bath. So what basically happens is by this attack of the acids, that mantle gets completely diluted and it gets evaporated. And now the leftover metal part will be used for our application. So this is how that is being done.
Thank you, sir.
Yes.
Okay, any more questions from the participants? Okay, I guess there are no more questions. Thank you once again, Shiva sir, for such a wonderful session.
Thank you, sir. Thank you very much. And I also would like to thank you for giving me this opportunity. And it was a privilege to be part of your program. Thank you. Thank you very much. And I always invite everyone for any sort of collaborative works to be done with us. So please feel free to contact us through the mail ID which I shared. So yeah. So thank you.
Okay.
Thank you very much.
Thank you, sir. Thank you. On behalf of the
Thank you.
organizing committee, I would like to once again thank you
Thank you, sir.
for
Thank you
such a
very much,
wonderful
sir. I would
session.
also like to thank Ashok for coordinating the entire process. Thank you.
Yes, sir. Yes, sir.
Thank you,
Thank you, sir.
Thank you, Professor. Thank you. See you.
Thank you, all the participants. So with this, we come to the end of the
Yes, sir.
first session of day 3. So I request all the participants to join us back again for the second session, which will start at 2:30, and the session will be handed over by the Tool Room and Training Center, Mr. Sofikur Rahman. He will be demonstrating. So thank you all for such a lovely interaction, and hopefully we will join again on the second session of day 3. Thank you.